Okay, welcome back. And we're in problem 8.3 now. Basically, we have three or four problems, and we're done with this chapter. And then the next time, I will do problems just from the end of chapter, from basically select problems of chapters 7 and 8. And that's the end of Newton's laws. And then we will start chapter 9 and 10, which is work and conservation of energy. Okay, so that's where we're heading. So now in this 8.3, it says, what is the maximum speed with which a 15 kilogram car, I think 1500 kilogram car, I would imagine. It turns out that the mass doesn't really matter. Yeah, it is actually 1500 kilogram car. So let me just correct that. 1500 kilogram car. What is the maximum speed with which a 1500 kilogram car can make a left turn around a curve of radius 50 meters on a level road without sliding? And then they say, assume that the force of static friction is 1. So if you drove or maybe rode with somebody who drives quick, fast, sometimes when you try to make a turn, you hear like a squeaking noise. The tires are about to start sliding. You feel like you can't quite make the turn if you go too fast. So let's imagine here's a car and it's going around like this. It's about to make a left turn, like that, or like this. So let's say the car is here and trying to make the left turn. So let us for once draw the car in here. It doesn't matter. So the circle is going like this, all right? And here is the car, and the car is going into the page. Here are the tires of the car, right? Into the page, into the board. So it's going into the board and going around, so it goes like this. So imagine it's going in a circle. So this is the radial direction. That's R, the radial direction. Remember, the radial direction is always from the point, from the mass, the particle, to the center of the circle. What are the forces involved in this? Well, there is gravity, mg. There is the normal force, n. And then there is some force this way. You need a force this way. You see, there is no motion in this direction, up and down, right? And that's the z direction, by the way. There is no motion in that direction. The car is not rising, it's not falling, it's just on the level ground. It's not going in this up and down, but it's going around the circle. And it's changing its direction. So somebody has to accelerate it, and that acceleration is toward the center. We know that. If you're going in a circle, there is acceleration toward the center. And we know from Newton's law that there is an acceleration if and only if there is a force. So if there is a force, there is an acceleration. If there is an acceleration, there is a force. So there must be a force that causes that acceleration. And what could that force be? Earlier, when we had that energetic father spinning the child, it was the tension in the rope. If you have a planet going around the sun, or maybe a satellite going around the Earth, it would be the force of gravity. There is no rope tying them. In this case, the only force of gravity acts downward. So the only force that could possibly do this is between the tires and the road, and that is the force of friction. And it is force of static friction because remember, kinetic means here's a surface, here's another surface. If I do this, there is a relative motion between two surfaces. That's called kinetic friction. However, if I just rotate my hand, each point just does not rub against the board. And so this is static friction. If I'm rolling, that's static. If I'm rubbing, that's kinetic friction. The car's tires are not sliding relative to the ground. Therefore, it must be static friction. That's called force of static friction. Those are the forces involved. Okay. So in this, in the R direction, that's the R direction, and this is the Z direction. That's what we call the Z direction. And if you're wondering what is the T direction, it will be into the board because it's tangent to the circle counterclockwise. So this is the R direction. So if the car is about to start sliding, it means the force of static friction has reached its maximum. Remember, force of static friction takes values between 0 to some maximum. So if the car is about to start sliding, it means we have reached the force of static friction, that is maximum, F static maximum. And remember, force of static friction maximum is equal to mu s times the normal force. And the normal force in this case, there is no motion up and down, and so the normal force has to equal to mg. So it is equal to mg, so it's mu s mg. Okay? So we know that, so now the net force in this radial direction, r, will equal to the mass times the acceleration in the radial direction. The net force, there is only the force of static friction, so it's mu s times mg equal to m times the acceleration in the radial direction. The radial direction, we know if it's uniform circular motion, the acceleration is v squared over r. V squared over r. And remember I said the mass would not matter, and it does not matter. It cancels anyways. So let's solve for v. So we get that v will equal to, multiply both sides by r and take the square root, so it would be mu s times g times r, and you take the square root. Notice, you have no control over g. If you're on Earth, g is what it is. It is what it is. It's 9.8, so you can't control that. So how can you navigate a curve faster without skidding or sliding? Well, if you have larger static friction, coefficient of static friction, it's not slippery, it's a rough road, then you can navigate it faster without sliding. Or if you want to go faster, so make the curve larger. So if you want to go through a tight turn, that's harder than going through a larger turn. So if the turn is, let's say, a mile of radius, that's easier to navigate than a turn that is just 50 feet. Okay. So in this case, it's 50 meters. So let's substitute. Mu s is 1, g is 9.8, and I have a 50 here for the radius. Let me get my calculator. So I have 9.8 times 50. Oops. 9.8 times 50. I get about 22 meters per second, approximately, roughly 22 meters per second. 22 meters per second. So that's how fast you go. You can go. If you go faster, you will start to skid. If you go slower, no problem. Friction can accommodate for that. Friction would be slightly less. The force of friction takes values between 0 all the way to something, to some maximum thing. All right. So to get around this, people make, instead of, when you get into the freeway, you notice the curve is not just flat and it's horizontal, it's banked. It has an angle. You get into the freeway and it's kind of banked like that. And that is to get around the fact, so you don't need the assistance of friction, which is the next problem here. So it says a highway curve of radius 70 meters is banked at 15 degree angle, and it says what is the speed v0 that the car can make this curve without the assistance of friction. So we have the radius is 70 meters, we have 15 degrees, and we don't want friction to enter. So the friction could be 0. The coefficient of friction could be 0. So we want to navigate the curve. So we want to go around the curve again, and then we're going around the curve, but the curve is banked. So here's how it looks like. So here is the car. The car goes around the curve, and the curve is banked. So it's part of like a big circle. All right? So this is R. That's R. So this would be my radial direction. And so what are the forces that could possibly be applied on the car? Well, the car is on Earth, and this is the ground. So Earth pulls it straight down. That's mg. What else? What else? Well, there is a normal force, and normal force is always perpendicular to the surface. What else? Think about it. Is there a strain? No. Is there a friction? No. Are there springs? No. So that's it. Don't come up with new forces that do not exist. And we have this angle here. Let me put the calculator down. This angle here is theta. So the car is constrained to move in a circle. Notice the car does not slide down the incline. It does not slide up the incline. It just stays at the same level. It will maintain that same height, but just go in a circle. But it's just bent like that. So in what direction is the motion? Well, the motion is only, there is motion only in this radial direction because you're going in a circle that is radial. But the car is kind of bent like that. So those are the only two forces. So what can we conclude? So who is giving us this force toward the center? Well, it must be the normal force, one component of the normal force. So first of all, there is no motion up and down, and so the conclusion is that mg, you see, if you have a net force downward, you will start to slide down or maybe slide up. So the mg must be completely eliminated by this part of the by the normal force. So let me break the normal force into two components. So if this is theta, this is 90 minus theta, and so this is theta also. So this is theta, right? Theta, those are two parallel lines, so this is theta. And these make a 90-degree angle, so this is 90 minus theta. And these two make a 90-degree angle, so this is the complementary to that, so it has to be theta. So let's break the normal force here. This part of the normal force is the normal force, it's the adjacent, so it's the normal force times the cosine of theta, because it's the adjacent, and this part of it is the sine. So this is the normal force times the sine of theta. So again, there is no motion in the up and down direction. There is only motion this way. So if there is no motion in the up and down direction, it means the net force in this vertical direction has to be zero. And so what are the forces in this vertical direction? Well, there is the mg, and then there is a component of the normal force that's equal to this. So you got the normal force in the vertical direction, and cosine theta minus mg equal to 0. So we get n cosine theta minus mg equal to 0. So we conclude that n times the cosine of theta is equal to mg, and therefore the normal force will equal to mg divided by the cosine of theta. Make sure you ask me in class if you're confused about this. Remember when we had something sliding down the incline which said the mg is larger than the normal force. Here, the normal force is larger than mg, because this is constrained motion. We're told that the motion is in a certain way, and the forces have to be in a way to make it happen. So the normal force has to be larger in this case. Right? Remember, normal force comes from the surface, and it's as much as it needs to be to make the motion, whatever motion that you have, happen, assuming that the surface could support the thing on top of it. All right, now, we have, in this direction, we have the component of the normal force this way, in the radial direction, the net force in the radial direction will equal to the mass times the acceleration in the radial direction. The net force in the radial direction, there is only one force, and that's the normal force sine theta. There is just this component. So that's the normal force times the sine of theta will equal to the mass times acceleration in the radial direction. Radial direction, the acceleration is v squared divided by r. Okay, let me go here. So I have n sine theta, but what is the normal force? The normal force is mg over cosine. So I have mg over cosine for n times the sine. So let me do it here. So I have, let me write it this way, mg over cosine theta, that's the normal force, that's this part, times the sine theta, times sine of theta, equal to mv squared over r. Again, the mass cancels. Sine over cosine is tangent, so this is g times the tangent. So it's g times the tangent of theta equal to v squared over r. Multiply both sides by r and solve for v. So you get g times r times the tangent of theta square root. Right, well, let's substitute. So we get v, we equal to 9.8 times r. R is 70 meters times the tangent of what? 15 degrees. Square root. Let's get my calculator here. So I have 9.8 times 70 times tangent of 15. And you have to take the square root of that. I got 13.56, about 14, approximately 14 meters per second. Let me just put 14. So, if this car goes at exactly 14 meters per second, it will make this curve without even friction, even if it's perfectly slippery. And then, so suppose it's perfectly slippery. If it goes at 14, it will make it. If it goes at slower rate, it will start to slow down. If it goes at a faster rate, it will start to slide up. It will make the radius larger. Because if you go at a larger speed, you will have a larger radius. Okay? So that's that. All right. Let me go to the next problem, and then we'll discuss some conceptual things. So here is the next problem here. It says a Stone Age hunter places a 1 kilogram rock and swings it in a horizontal circle around his head with a 1 meter long vine. It says, if the vine breaks at a tension of 200 newtons, what is the maximum angular speed in RPM with which he can swing the rock? Okay, so I cannot get you a Stone Age hunter, and I cannot get you a rock, and I also can't get you a vine. But I got you myself. I got you a string, and I got you a piece of metal here. Let's say this is 1 kilogram. Let me try this so I don't hit myself. I'm not spin it around my head, so I'll just give you a horizontal circle. Here's the rock, well, the mass. It's going in this circle like that. That's the circle, and it's going like this. It's like so it spans like a cone. It's like a cone that goes like that. Right, so it's a cone, and so it is going like this. Okay, so what are the forces involved? There is the tension, and then there is the force of gravity downward. So let's draw this. Let's see. So it's tied here. This is length L. And this is the mass, and the mass is going around the circle. It's going around the circle. It's going around like that. This is a circle of radius r, and this angle here, let's call it theta. What are the forces involved here? What are the forces on this mass? Well, there is mg, gravity. What else? There is the force of tension along the rope. Here's the force of tension. By the way, if this is theta, then this also angle here is theta. And that's it. Those are the forces. So we need to include all the forces, but don't make up any forces that do not exist. Get my keys out. So the action is around this circle. The stone doesn't get higher, and it doesn't get lower. So there is no motion in this direction. So the net force in this direction has to be 0. There is mg this way. So the component of the tension that's this way, this component of tension, let me call it, since it's the adjacent, it would be t times the cosine of theta. That's the component upward, and there is mg downward. And then the tension also has a component in this direction. That's the one that causes the circular motion this way. So this is t, since it's the opposite of the sine of theta. So in this vertical direction, it will be in that z direction, if you will. The net force, let me call it the net force, in that z direction is equal to 0, because there is no motion in the z direction. You have two forces, you get t cosine theta minus mg, right? T cosine theta upward and mg downward equal to 0, and therefore we get the fact that the tension would equal to mg over the cosine of theta. You might say, I don't have the angle. That's fine, we don't have the angle, but let's work like this. We have the length here, so we will work with the angle theta, and then we will relate it to the length and tension and r. That's fine, all right? And then we will go to the radial direction. The net force in the radial direction, the net force in the radial direction will equal to the mass times the acceleration in the radial direction. I know there is acceleration in the radial direction because it's going in a circular motion. The acceleration I know ahead of time that it's v squared over r, and v squared over r, it's uniform, v squared over r, whatever r is. And the net force in the radial direction, well, there is only this component of the tension, it's t sine theta. T sine theta. But t is mg over cosine, so you would have mg over cosine times sine, just like what happened earlier, would be tangent. So it would be the tension times mg times the, I'm sorry, do I have the stone? Yeah, that's okay. Yeah, that's fine. So I would have the tension times the sine of, yeah, so it would be mg times the tangent of theta equals to mv squared divided by r. Yeah. The mass cancels, and so I get the following. So I get v squared will equal to g times r times the tangent of theta. And so I will take the square root of both sides. I will get gr times the tangent of theta. But what's the tangent? What's the tangent of theta? The tangent of theta is the opposite over adjacent. Opposite over adjacent. And opposite over adjacent, or sine over cosine, sine of theta over the cosine of the sine of theta over the cosine of theta. Okay. Let's see. And since I know ahead of time, if I knew theta, I will figure out the tangent of theta. So let's use this one here. I should have used this, because I know the tension, I could figure out what the cosine is. Let me use this one. So cosine theta would be mg over tension. Yeah, let's do that. Cosine of theta is equal to mg divided by the tension. And so theta will equal to cosine inverse of mg over the tension. Okay, so we cosine inverse of mg. The mass of the stone is 1 kilogram, g is 9.8, and we're told that the rope is about to break. We're going it fast enough that the tension is 200 newtons. 200 newtons. And so I get theta. Let me get my calculator right here. So tangent of 9.8, tangent inverse of 9.8 over 200. So I get 2.81 degrees. 2.81 degrees. That'll be the theta. And let me just double check that I actually have the right angle. I don't want to continue if it's incorrect. Indeed, my angle is correct. Good. Otherwise, we have to do the problem again. Again, I do these problems like this. I don't check the solution so that you see me struggle in reading and understanding the problem, and then actually applying the physics, Newton's laws to solve it. Okay, so we have that. So let's go here. So what is R? Well, if theta is 2.8, then R will be the length of the string times the sine of theta. Yeah. So I have the following. So V will be, let me rewrite this, will be G times R times the tangent of theta square root. So I get V will equal to G times R. But R will be the length of the string, which is 1 meter long. 1 meter long times the sine of theta. So it'll be the length of the string, which is 1 meter, times the sine of theta, and then times the tangent of theta. Now we can substitute. We know everything. So G is 9.8. The length is 1. And then sine of 2.81 degrees times the tangent of 2.81 degrees. Okay, so let's get V. Okay, let's see. Let's see, so I have 9.8 times the sine of 2.81 times the tangent of 2.81, and then take the square root of that, and I get V equal to 0.15. I actually made a mistake here. I just checked. I mean, the angle is close to 0 here, so this should be close to 90. I think I plugged tangent inverse earlier. Let me redo it again. Sorry about that. Let me do cosine inverse of 9.8 over 2.81. Cosine inverse of 9.8 over 200. Okay, 87.2 degrees. That's way, okay, makes much more sense. 87.2 degrees. Okay, now this would be 87.2 degrees. And this would be 87.2 degrees. Yeah, otherwise I get a pretty tiny number for the speed. Okay, so now let's see, 9.8 times the sine of 87.2 degrees times the tangent of 87.2 degrees, and then you have to take the square root of that, and I get 14.15, about 14.2 meters per second. But that's not that they, the end of it. They would like to know what is the RPM, how many cycles per, how many revolutions per minute does it make. So I know that that's omega. So I know that V is omega times R. So omega will be V over R. And so that would be this number here, 14.2 divided by R. So it would be V over, remember, R is L sine theta. L times the sine of theta, so it'll be about 14 point, let me not round then, 14.115, let me put 14.15, 14.15, not going to round, and then L is 1 times the sine of theta, which is 87.2 degrees. So let's see what omega will be, this number over the sine of 87.2. So omega would be about 14.16 radians per second, and we need to change that to revolutions per minute. So omega, which is 14.16 radians per second times 60 seconds per minute times 1 divided by 2 pi. 135 revolutions per minute. Let me make sure that my number matches. Yes, it does. So I have to put 135 revs per minute. All right. So now finally, after a few mistakes, but that's fine. That is the process of problem solving. Mistakes will happen, and you have to correct them. Just double check. I mean, if you got a really tiny number, I think I got a few meters per second when I used the wrong angle. I think I got like 1 or 2 meters per second, but that's really slow. That's not going to break it. So I figured that it has to be much faster than that. Okay? So now, we'll get in the next video.